Good evening, everyone. Sorry, I'm running a little bit late. My kids absolutely did not want to fall asleep tonight, so this is a little bit rushed. Means I also don't have an editor yet. So my plan for tonight is to continue some work that I've been doing in the last couple of weeks, and that work started from the observation that PyPy 3 often has a somewhat worse I/O performance than CPython 3. And in particular, it also has somewhat worse I/O performance than PyPy 2. In PyPy 2, we did fairly careful work to try to make sure that I/O performance is quite close to what CPython provides, because in many programs, you're not only CPU bound, but you also, usually you read some kind of input, and it's bad if the input reading part is like many times slower than in CPython, because that means it will eat up all the benefits that the JIT provides. And some of these, from Python 2 to Python 3, a lot of the ways that I/O was done changed, because in Python 3, the I/O implementation switched to a custom implementation in CPython. I think before they used a standard I/O implementation, and afterwards they switched to this custom tower of streams exposed via the I/O module. And PyPy has always used that tower of streams approach, but we have two versions of it. The one that's used in PyPy 2, and then a kind of new one in PyPy 3. And not all of the optimizations of the PyPy 2 one have made it to PyPy 3. And one of them, a few of them I tried to look into in the last couple of weeks. And a new one, one of the remaining ones, I'm going to try to look into today. And let's see, there's an issue for that. The issue is right. This is the general shape of things. You open a file, you go over the lines, and you don't do anything with the lines, because just creating the string is enough work, and then you're done. And so it used to be quite a lot slower, and nowadays it's okay, but one thing that is still a lot slower on PyPy 3 than on PyPy 2 is just the opening and closing of the files. And I want to look into that tonight. Hi Tobias, good to see you. Right, so let's start with a very simple benchmark. I think I have one. Let me check. Oops. Or not. Here, maybe. Right. Hi, Matti. Good to see you as well. Right. Yeah, I think this is the benchmark that I want to look into. It's really very simple. You give it a number of iterations, and then it just opens. It opens file, which is the current file in reading mode. We could even use binary, open it in binary, because that's even less work. And then we don't do anything with it, and so it's just being closed again. We do that many times, and then compute the time it takes. Let's try that. Yeah, let's. As I said, I'm somewhat less prepared tonight. Right, so let's open it in binary mode. That does slightly less work when constructing the stream tower, and let's try it. So PyPy 3, open many, I'm not sure whether 10,000 times is enough. Let's do 100,000 files. Right, that takes a second. As I said, it's really just opening and closing the file, not doing any work. And CPython is twice as fast. That doesn't sound completely terrible. but PyPy 2 is like 5 times faster on this. Let's like add a 0. Of course, I mean, as usual, benchmarking on the stream is quite dicey because my CPU is quite busy actually streaming stuff and transcoding my resolution down, and so we should take these numbers with a grain of salt, but it still looks like roughly a factor of 5, which isn't good. And compared to CPython, right, 2 times slower than CPython, which is not a huge problem, but let's fix it. I mean, opening files is a relatively common operation, and the first step in fixing it is that I'm running the call grind profiler. I did that once before, and it gives really weird. It gives really weird results, if I remember correctly. Call grind. Right. So, I mean, it's always a choice on which level you want to do profiling, but given that I want to look at stuff that's happening in the implementation, the val grind, which is like an assembly or a C-level profiler, is the right choice, because if I use the Python profiler, we can do it just to see it. If I use the Python profiler, it would just show me that all the time is spent in main, and then maybe it points at the open built-in, but it doesn't really tell us what is slow within the open built-in. Right. And that is what we can look at here. And right, so let's sort by self. Right, and here, so this is a fairly weird result, but it gives me a huge hint, and it means that we will look into a somewhat strange part of PyPy tonight. We see that the top 4, maybe 5, right? The top 5 entries here are actually in the garbage collector. So trace is a garbage collection function, trace and drag out is a garbage collection function. Then there's the incremental minimal garbage collector, visit all objects step, that's part of the garbage collector. There's another trace function, part of the garbage collector. Memcopy is called from many places, but here we can see that it's also called from the garbage collector. So something's weird, because, I mean, creating 100,000 objects is absolutely no problem for the GC, right? So creating and throwing out 100,000 objects should be extremely cheap, and the fact that it's not here gives us an indication that something slightly weird is going on, right? And actually, this next entry gives at least me the next indication what the problem is. And I mean, unfortunately, the function name is cut off. It says incremental minimal garbage collector, deal with objects with fin. And so we can grab what the fin means. So the garbage collector is in the rpython directory. Here, I think. No. Memory to see. Right. Deal with objects with fin. Right. And here we see what the full function name is. It's deal with objects with finalizers. And so what are finalizers? Finalizers are things like __del, which are called when an object is dead, is discovered to be dead at the next garbage collection cycle. And now, I mean, at least at that point, it became clear to me what's going on when I looked at this previously, which is the fact that where's my benchmark? Here. These files that we're opening here, they have an __del method. The reason for that is, if you forget to close them, you want them to be closed eventually by the garbage collector. Right? You shouldn't rely on it. I mean, it's best practice to never rely on the fact that your objects are your files are closed by the garbage collector, because you could run out of file descriptors, but they still do have a dunder del. So the GC is somehow involved, and we can just for comparison, we could run the same benchmark with PyPy 2. And I kind of suspect that there we don't see this function. 217 7851. Right, we don't. We see weird things from the linker, that's from startup or something, right? And then we see things that belong to file reading. It's kind of interesting that we see a read. Did I run the... Why do we see a read? It's not quite clear to me why it would read anything. I don't know. Maybe those are unrelated file reads that we run when starting up the interpreter. I'm not entirely sure. But we don't see garbage collection stuff, and that, I mean, we do, but it's further down in the. It's much further down in the profile. So something's weird. I mean, in PyPy 3, some essential optimization got lost around garbage collection of files, and I wanna look into that. And so for that we need to. I mean, garbage collection in CPython and PyPy and in general in Python-like languages is pretty complicated. And I mean, the basic idea is that you can define a del method, and the del method is called when the object dies and is collected by the garbage collection. And there are many complications around that. The first complication is the del method is just a regular method, so it's called. So it cannot be called from within the garbage collection context, because at that point the heap is in a slightly weird shape. We need to run it at some point later from some Python thread. And so there's some enqueuing happening. And another really weird side effect of dels is that the del method can actually resurrect the object. So if you have a class with a del, and then it's absolutely fine to say global x equals self, right? And that means that after running the del method, the object is reachable again. So the garbage collector must not actually free it, because otherwise we would have a problem. So if we allocate a few of them, let's just make some. And then we can call the garbage collector. Right. So now we have an X. So the garbage collector ran, and it actually stored this one here into the global X. And I suspect that if we run collect again, right, this del here ran and overrode our X. So I mean that's certainly something to be kind of wary of. You can, if you run the del, you need to basically check again whether the object is still dead. And in CPython, it's even the case that, I mean, it used to be the case that you would run the del many times. So let's say you kill an object, it dies. You kill it. It's no longer reachable. So the garbage collector reclaims it. It runs the del resurrects the object. Then it lives for a bit longer, then it dies again, then the del is run again, and then it can enter this weird cycle where the object is just continuously resurrected and the del is called. This used to be the case in Python 2, but then at some point this proved to be the source of quite a number of bugs. So PyPy very early on decided that we would have a slightly different semantics of calling the del of an object at most once. And the reason why PyPy does it that way is that PyPy doesn't have reference counting, so we cannot actually cheaply determine whether the del resurrected the object or not. That means after we call del, we cannot know whether we should call del again or not. So, I mean, after we call del, we just keep the object around, and at the next collection we will reclaim it, but we don't know whether it was resurrected in the time between the two collections. And that's the reason for why we don't want to call the del a second time, because we can't determine whether we have to or not. So we decided to at most call underscore del of an object at most once, and then CPython switched to this approach some versions later. Right. So this is about objects with with del, right? With user-defined underscore del methods. But classes are more complicated. Files are more complicated. I'm not entirely sure whether files have a del. Let's actually check that. If I open a file, I don't know, like this one. I'm in PyPy 3, right? Does the file method have a del? It does. Okay, great. Right. So it does have a del. So right, and that means if you make a subclass of IO base or buffer reader and you define your own del, you want it to be called, right? And so what I think happens in PyPy 2, and I basically wanna check that. Okay, this is some random branch. It's not. Matti suggests to have a debug print that shows me when the benchmark starts. That is great for when we want to, that's a very cool technique when we want to read the JIT logs. But in this case, we would have to be able to communicate with the profiler to say, please only start profiling now. And I don't think there's an easy way to do that to Valgrind. Maybe there is some API, but I don't think we expose it to PyPy in any way. Right, so let's try to see how this works. Where are our files even? Right here. File interp stream module def. Right. So this is PyPy 2. Right. So now I need to remember where the weird thing with finalization is going on here. Do we import the GC here anywhere? No. GC. Only there. How did it work? This is, I'm not even sure I was ever involved in writing this. I just, in Q. Okay. So what happens if you close a file? That's not here. Right, there's a close here. Right, I think this is what we need. So let's think back to our benchmark here. We know that file objects have finalizers. They have a dunder del, but you don't actually need to call the dunder del because the dunder del under some conditions is actually a no-op, and in particular the dunder del of a file object is a no-op if you have explicitly called close of the file, right? So if you open your file, if you say, where is it? If you open your file here, and then you say f.close, it's not actually necessary to still call the dunder del of f, because del only closes it, and it's already closed, so del doesn't do anything. And now we have a kind of a weird API that says, okay, if you closed the file, there's a way to tell the garbage collector you do not need to wait for this object to die anymore, right? Because the garbage collector actually has a list of all the objects that potentially need finalization, and after every collection, it needs to go through this list and say, did it die? Did it die? Did it die? Did it die? And that's a lot of work. So if you're sure that an object dying doesn't actually have consequences because the del is a no-op, like in this case here, there's an API in PyPy that says, please ignore the finalizer for this object now, because we know that it won't do anything. And that's the API that is used in PyPy 2. And that's called here. So in close, we check, do we still have a stream? Like, is it still open? And if we do many things, like we unregister it somewhere, we close the underlying stream, we do all kinds of various things. But in particular, we also call this thing, may unregister rpython finalizer. And I'm very sure that this is what we're missing. Right? And this, I have no clue where this comes from. Which here is PyPy 2. Let's grab for it. There are a few places where we call it. And I suspect that it's always called from close methods. Let's actually check that. Let's check interp zlib, for example. Right. Interesting. It's called from flush. Why flush? Because it's called from flush if we say finish, which I suspect is like close. Right. So if we close the zlib stream, we can also say you don't need to call del of the stream anymore. Right. Let's look at one more example, like socket. Right, and in socket it's similar. We call close on the underlying socket, and then we say may unregister rpython finalizer. That means we tell the GC, you don't need to watch this object anymore. Its del will not do anything. Right, so let's actually look at where is it implemented. It comes from the base object space. And I suspect that it comes from we have this ultimate base class that all the classes that represent Python objects inherit from, and that is called wroot. That's basically the wrapped root class. This is the abstract root class of all wrapped objects that live in a normal object space like standard object space. Right. And it doesn't have any data. It just has things like it just has a couple of class attributes. And so there is here. Right. So optimization hint only. If there is no user-defined del method past the hint, don't call any finalizer to RGC. Right. So we get the class of self, and then we ask the class, do you have a user-defined del? That's a flag on the class. And if we do not have a user-defined del, then we can say, we can tell the garbage collector via this rpython rlib, like the restricted library, RGC modules, and call this function may ignore finalizer. And that's great, because if you tell the garbage collector that it may ignore the finalizer, it can unregister the object out of this global list of things that have potential dels, and then the del simply won't be called. But that's of course only safe if you do not make your own subclass of file that has a user-defined del method. So I'm actually very curious how this thing is is defined. Let's actually check that. How does it know that it's a user-defined del, right? I think it's in here. Oops. No. Right, it's in type object. Here. Right has user del. Where is that from? It's false. Right, if one of the base, so this is subclassing, if one of the base classes has a user del, then we have a user del ourselves. That makes sense. Right. So here it says this. If a del in dict has user del. But now I wonder, because it's possible that we have a bit of a problem. The problem that I'm foreseeing is that, so in PyPy 2, oops, it's just called PyPy. In PyPy 2, if we open a file, or we can use file, test all.py in binary reading mode, does it have a del? And the answer is no. And so we might have a bit of a problem here, because I'm not sure. So in the PyPy 3 case, the streams do have a del, right? So this check here won't work. This check here that says, where is it? Before we unregister the thing, this check here that says, do we have a user del? Ignore the finalizer. That's always going to be, as user del is also always going to be true. That means this will never be reached. That means we won't get the optimization. And so we need to be a bit careful of how we, how we circumvent this problem. So let me think. Yeah, I mean, this will come and bite us. So we should definitely invest in some thoughts of how do we actually make sure that user-defined subclasses of the stream still have their del called, but normal like unsubclassed stream classes do not have their del called. Right, I have a window here. Let's actually go there. This is PyPy 3 now, and let's go to the I/O module. And the I/O module has a number of classes we can grab for del here. Right, so I/O base has a del and none of the others do have a del. Right. And there are complicated comments here. Maybe I should actually read those comments. So what does del actually like? Okay, let's look a bit. So del, so this is the definition of the type, and the type says it has a del, and that means that the del is mapped to this Desker del method, right? And so when the file is finalized, we call this thing here. So what do we do there? We say we check whether we're closed, and if closed doesn't exist or can't be evaluated as bool, then the object is probably in an unstable state, so ignore. Right? So if there's no closed attribute and we get some kind of error trying to find out the bool value of closed, then we just don't do anything. Otherwise, we call dialog warn w, right? Right, so this is a method that's only called when we were closed via the deconstructor, and that will warn us that, oh, you forgot to close your file, please do so later. Let's try to hit that. So if we're in PyPy 3, let me open this a few times, and then we collect. I think it's not the font. Matti complains that some underscore methods are invisible. We don't get a warning. I think it's turned off by default. You need the developer mode or something. But this produces a warning in some of the modes. So I think the problem is something more annoying. It's the fact that the window is slightly too tall. Let me try to fix it. Resize. This is not better. Thank you, Ubuntu. Can I hunt the pixel down here? Okay. I'm on it. Right. No, it's really it was a bit too tall, and then the lowest line was actually enough pixels down the screen that you didn't see just the underscores. The rest was kind of readable. Right. I'm curious how. I mean, I'm getting a bit distracted, but I kind of want to know briefly what the dialog warn actually does. Right. So dialog warn. says it uses a resource warning to say unclosed file something, and that happens only if you close the file via if the file is closed via a dunder-del. That means you didn't use a context manager and you didn't call close explicitly. Right. Okay. Anyway, that wasn't what I. Oops. Now I very carefully positioned my window, and then I accidentally closed it. Fantastic. Right. No, I should set the font first because otherwise, as I said, I'm slightly unprepared tonight because the kids really didn't want to sleep. That's okay. It's still visible down there. It's a bit too wide. Right. Okay, sorry about that. So we wanted to be in the I/O module, and let's look at I/O base here. Right. So the problem that we have is we do have a del, and we need to ignore that del, right? But we must only do that if it's not user overridden. And I think it's, I mean, there are two approaches here. One approach is that we could just not use the API that's there, right? There's this API may unregister our Python finalizer, and it calls a condition that is wrong for us, right? So one approach is that we're not calling this function. We could call this thing here explicitly. The other thing we could do is we could change this function to also check whether we have a user overridden subclass. Could also work. Maybe somewhat more risky because it would affect all the other affect all the other users of this API as well. So maybe let's not do that. Let's instead call this slightly lower level RPython API ourselves in the I/O module. Okay, before we do that, as usual, we need to think of a way to test this, right? So it has a okay. What test files are there? Let's use file.io. It's fine. Lots of stuff. Maybe we can actually find, I mean, I wonder whether whoever implemented this in PyPy 2 actually wrote tests. So let's actually go here and do a little bit of blaming and to find out whether there are any tests here. Wait, where was it? Which interp file may unregister? So it was Armin who wrote this, then not entirely surprising. And it's done in this commit. Right. And there are no tests. Armin is not getting any cookies. Right. Oh, cool. It's done in generator iterators as well. I mean, so if you actually, if you finished iterating and then you don't need to call the dunder-del of the generator iterator. If you forget it, then you will get some exception, I think, raised during garbage collection. And they are also using the underlying API directly, so there is precedent for that. That makes me feel slightly better. Right. Yeah. So my plan is I wanna do the following. my plan is the following. We can't really test this with the GC easily. So my plan is something like we at least make sure that where is it? We make sure that this function is called by stubbing that out and having a test that checks that we see a call to it when we do when we call close, but also making sure that we don't see a call to it when we have a user-defined subclass of the stream object. Let's try it. So anyway, this is like even just closing the files is much more complicated, right? Because there's a stream of there's a stack of these streams. So I think we even go along like some chain of streams that and each of them calls close on the next. Let's look at close for a little bit more closely. Pun not intended. Right. So if we're close, we don't do anything. Otherwise, we call close and we call flush. Why in that order? That sounds strange. There's buffered IO, and that what does it do? It tries to get it gets the lock. If we're close, we're done. Otherwise, we call flush, and we call close on the raw stream. And the raw stream is then another stream which might close on yet another thing, right? So closing is really on the complicated side here. Okay, so let's try the let's try to write the test. The test has to be written on the RPython level. That means it's in Python 2, and right, we do stuff like this, right. Flush at exit IO error and value error. Interesting. Right. Okay, that's a fairly weird test. So what you test is, so before you exit the process, all the remaining open files are flushed, and there's a problem that if your flush raises an IO error or a value error, then it used to crash. I suspect that's what the test is for. It used to crash, and so yeah, we don't want it to crash. So this is the test that makes sure that no crash occurs. Bye Tobias, good to see you. Right, and I'm not sure we do it like this. There's another flush at exit here, right? Here this checks the flush at exit. We open a file, we write something to it. We don't flush. We keep the file alive. Then we call finish, which simulates the closing of the interpreter, and then we check that when we read the file, we see the write. Okay, and we want something like this, I think. How do you monkey patch something from PyTest again? I keep forgetting that. PyTest monkey patch. It's a fixture and it takes a set utter. Okay. So we get the monkey patch fixture, and then we say from rlib import rgc, and then we say monkeypatch.setUtter, right? What's it called? It's called make-nor finalizer. And so we stub it out. So we need to define it. And what kind of arguments does it take? It takes an object. And now what we basically want to test is we want to open we want to make a stream object, then we want to close it, and then we want to check that we get one call to that, and then on the second close we won't get another one. But yeah, that's the most basic test that we want to see, and it will fail, of course, because we don't ever call this on streams so far. Right, let me think. How do we make a stream? Can we just make a... We can just very manually make one. IO base. I'm confused. Ah, wait, I'm in the wrong file. Interp IO is where I need to be. IO base. Right. Okay, so that's IO base. Let's make that. So from module PyPy .io interp IO base import w IO base. We can make an instance of that, and then w base. I'm not even sure is it instantiatable in CPython? I'm not sure it is. Import IO base. Can I make that? I can. Very useful. Right. What kind of methods does it have? Right, we can flush it. Does nothing. Is it readable? No. Is it writable? Seekable? What good are you? No, there's no writable. Ah, no. Right. It's a very useless object, but you can close it, I suspect. Right. Many times. Good. Wait. No, wait. Now I missed the most important thing, of course. Does it have a del? It does. Right. Okay. Right. So we make an IO base. We do everything on the RPython level. So on the RPython level, or I mean, as we saw on the Python level, the constructor doesn't take anything. But on the RPython level, the constructor of basically almost everything needs a space. And then it even takes a second thing, add to auto flusher, and we say false. Because it's just a test thing, we don't need to flush it. I suspect that flush is also a norm, right? Yeah. Right, and then we say close. What do we call close? Close W, which also takes a space. And now we want to say assert calls equal base, right? After we called close, we know that we don't have to call the finalizer of this thing again. And the reason why we know that is because close is already called. The finalizer, like the del, would just call close again. So we don't need to do that. And so this is the first thing that should happen, and it won't, because may ignore finalizer is never, I mean, it's nowhere in the code base of IO base. So let's start the test. It will just fail, but I like seeing my tests fail. Fail first. Where is it? File IO. Right. While we run for that, while we wait for that to fail, we can write the second half of the test. So there's a few more details, like if you call close twice, then you will not, you shouldn't call may ignore finalizer a second time. It doesn't matter. I think you can call this function as often as you want, and the GC will just ignore subsequent calls. But let's be tidy and not do it. And then the more important part is actually that now we want a user-defined subclass. And so now we need to say space.appexec, and it looks like this, I think. Right. I know we don't even need to pass it out. The only thing we need to make sure is that when we make a subclass, so import IO, and then we make a subclass of IO base, subclass with del IO base, and it has a del, right? The del does nothing, but we cannot analyze it, so we just need to know its existence, and then we make an instance of that, and then we close it. We cannot know that the del that we defined here isn't doing something nefarious, like resurrect the object or like write something to a socket or whatever. So we must call this del, right? So most importantly, we must make sure that executing this code here will not add anything. It will not call may ignore finalizer a second time, right? So we should make sure that the calls list didn't change. So we check that it's still the same as up here. So by the way, this appexec thing is a bit of testing magic. And I mean, as a reminder, we're running code on the RPython level here, so it's all written in Python 2. And then sometimes it's the case that you want to execute some code within the context of the interpreter that we're currently testing, right? I mean, all these tests are they're testing the interpreter. And so here we can say, please now run some Python code in the, please now run some Python code in the context of the interpreter. So parse it, turn it into bytecode, and then run it on the interpreter. So, and then, yeah, and then we're back on the Python, like from here on, we're back on the Python 2 level, the RPython level again. The ARM general says that I shouldn't forget the second equal. Thanks a lot. I tend to do that often. And I should probably turn some light on because it's getting dark outside. Right, so what does our test do? Right, the test fails. The test fails in exactly the right way. It fails by saying you didn't call this API that you promised to call. And so we didn't see a call to this thing, and so it fails here. That's good. I mean, running it again won't show us another failure because the execution stops here, now here. And this part would pass, right? Because we indeed don't do anything. I mean, here we test the absence of a call to may ignore finalizer, and indeed we wouldn't call may ignore finalizer. But yeah, we want to make sure that this part keeps passing even when we make the first half pass. Right. Okay, so now we need to do the work, and the work is here, I think. Right. So after all this stuff is done, yeah, let's actually look around a bit more. Yeah, because I'm slightly worried that all of these functions don't actually call. I mean, those inherit from IO based at some point, right? Yeah, this inherits from IO based, but I think the implementations of close are a bit bad citizens here, right? The implementations of close don't actually call the base close. Right? They do their own thing. So we may need to like introduce our own API somehow. Right? Yay, my channel is famous. There are people that spam me. Fantastic. Ban user. If I'm famous enough for spammers, I don't need to become more famous. Right. Good. Okay, so yeah, what I was saying is that the close method here doesn't actually call the base implementation of IO base. That's bad. That means we may have to put the new magic code in several places. Right. Okay, let's see. There's something here already. So I'm a bit confused. Maybe, we may have to do a bit of archaeology here. Why is there this thing that says needs finalizer can return false if we know that the precise close method of this class will have no effect? But then we don't, it always returns true, right? I think the reason is the warning, because even though the close method does nothing, we still want the warning to occur, right? So the warning that you forgot to call close. So it's indeed true that we need to always say to the GC, I have a finalizer. But then when we get the close, we can say, I have a finalizer, but it doesn't need to be called anymore. So so this needs finalizer thing here. I still wanna do some blaming and looking at the version control history here, because did this ever do anything useful, or is it just there for fun? Or I'm a bit worried. So let's see. HG blame interp IO base. Right. So this was it was added in this, but the return true has the same version as the whole function, right? So show. Right. Yeah, it seems something really something slightly weird goes on with the IO base class in CPython 2. IO base is the only class in CPython 3.5 to have both a TP finalize and be overridable. This gives semantics that are markedly different from the old less than 3.31 and that are closer to app level classes. See comments, right? Yeah, there's some slightly weird. Ah no, look here. There's an. Okay, I'm confused. Ah, right. Of course. I'm silly. What I should have checked is that are there subclasses that override this needs finalizer function, and there are. There's one here. And that's the buffered read-write pair, which is a fairly rare thing. And who else has its own implementation here? Bytes IO. Of course, the bytes IO. I mean, if you write into a string, of course you don't need to have a del. And string IO is the same, right? But none of the real file classes have this return false. Right. So we shouldn't ignore it. It's good that it's there, but it doesn't help us. Okay, what we want is I think we may want our may unregister final our Python finalizer IO. We want our own implementation of that. I'm not calling it the same thing because that's scary. But bye, Matti. See you later. Maybe I'll see you in the next days. Right. Okay. So what to put here? We need to be extra careful here. We need to be careful. I think the right kind of code is Let me think. Yeah. I think we should be very conservative to start here. We can be extremely conservative, and we can say something like, if this is a user defined subclass of any of the IO classes, even I mean I don't care whether it defines a del or not. If it's user defined, then I will just be on the conservative side and always try to call del. If it's defined in RPython and so basically under control of the interpreter, then we know that __ del will do the same thing as close. And so after closing it, the del will not do anything. So what we can say here is we get the type. So that's space dot. How do you do that again? Def may, right. Let's just do this. We get the type of self, and then no, it's even simpler. We just say if self.user overridden class, right? If it's a user-defined class in any way, then return. Otherwise, rgc dot unregister. What's it called? May ignore finalizer. Self. Right. So that's the API, and then now we need to call it. Right. And now we should basically change our test a little bit, because it's actually slightly more conservative. Whenever we have any subclass of the IO base, we will not call the dunder-del. We will not ignore the dunder-del, right? So here we have the API. We're not using it yet, and we're going to start to use it here by saying, okay, in close, what we do is we say self.may unregister our Python finalizer IO of space. Right. Okay, let's try that. Another typo. Yeah, I forgot the closing parents here. And thankfully, the armchair general told me to fix the double equal here, so I'm not getting a second syntax error. I'm getting some missing imports though. Here from our Python rlib rgc. Whoops, what's going on here? That is concerning. Why does the IO module not have an IO base attribute? Tab new. What am I doing wrong? It's underscore IO base. Right. Oh god. I really hope that... Okay, let me try something. What's the difference between IO base and IO dot underscore IO base? Is that the same thing? Oops. Seems not to be the same thing. Okay, yeah. This stuff is complicated. So right. So the one that's exposed via the non_IO module is anyway already a user-defined class here, right? So now I kind of hope that What about something? I mean, we don't really care about I/O based, right? We care about stuff like buffered I/O based and right. So we have a problem here. We have a huge problem here, but let's take it slowly. Let's do it step by step. So first we need to check fix the test. It's not I/O base, it's underscore I/O base, right? And so this should now hopefully pass. Let's run those tests again. So now we will unregister the del, the dunder del, if somebody instantiates I/O base from the underscore I/O module, which nobody ever does because the non-underscored I/O module has its own subclass of that, and that subclass will never do the unregister thing because it does have a del. It doesn't have a del, but it's a user-defined subclass. So we may have to be more precise here. But let's be very slow. And this is a good win. This is our first passing test. And so let's look at the diff. And this looks good. And yeah, we may be too conservative here by doing this, but we should before we change it, we should actually add more tests, and maybe we can commit this. Wait, okay, there is some white space here. So am I on the? Oops, see, I'm doing nonsense. Shelf. I was on some unrelated branch. As I said, extreme lack of preparation tonight. Branch by 3.7. Unregister. No, make no. Ignore finalizer files after close. Right. And now we look at diff. Diff looks good. Let's call it. Let's commit it. Oops. Right. Okay, first test, good. Now we want an equivalent test for various other configurations, and we need to be sort of quite careful about them. So yeah, let's think. I'm still. How does open work? I don't know any of this stuff. So I'm actually quite curious. Like the open built-in, what does it actually do? It's even defined on some weird place. It's exposed via the built-in module, but I don't know where does it actually come from. State get space what? Sorry. It comes from the I/O module, right? So the I/O module defines open. So we should be able to see open here, and that's in interp I/O. Open. So we do lots of things, and then various warnings. Where do we actually create the things? Windows 32. Here we open the file, here we call file IO, and then we wrap the buffering around it. and here, and then we wrap the text wrapper around it, and that's it. Okay, interesting. Right, so that's how open works, but that's really weird, because let me try something. So what we learned, what I just learned, I had no clue about this. So there is something like the buffered reader here, right? Oops, this thing. I should really open the standard libio module here, libpython3io. Here. So what is buffered reader? Okay. So buffered reader is actually buffered reader really comes from the _IO module. So it's just that's good. It's just that buffered IO base, raw IO base, and text IO base are subclassed here, and then we register them via, which is an ABC meta thing, I think. We register them and say buffered reader is a subclass. I don't know what the registering does, but it's somehow registered via these ABCs. Okay. So maybe we don't have a problem. So what I want to do now is I want to write it. I mean, what I really care about is those classes. I want to care about file.io, which has a del. I want to care about a dunder del. I want to care about buffered reader and writer, which have dels, and buffered random maybe, and text.io wrapper. And those should, those should ignore their dels after close is being called. I think that's what we want to do here. So we need to write tests for them. Let's start with something like file.io. Is there a file.io? Okay, how does file.io work? Interp file.io here. Right. So what does it do? There's a class here. Right. It's a file.io thing. It gets file descriptor set to -1, and it probably has a close, right? And what is raw IO base again? All these classes, I'm really getting lost in the IO module. So raw IO base is a subclass of IO base that adds something like read and read all, maybe based on read into. Okay, fair enough. Yeah, it's all very nice and very object oriented or something. Right. That's, by the way, that's also the reason why we get, I mean, now I understand this. That's also the reason why we get so many calls to dunderdel, right? Because every time we open a file, it's not just one object. It's like this tower of streams, and all of them have dels. So that means that if we open a text file with buffering and decoding and like file, we have 3 objects that have dunderdels, and that means, I mean, that's the reason why we get so many calls. Like, we really have the problem not just with 1 object per file, but with 3 objects per file. Right. Right. So let's start with let's restart with file.io. So we write a test here that looks. I mean, we don't even need to write it. We just copy this. Maybe we can find a way to write this more generically later, but let's write it in the boring way first. Now it feels slightly weird to have all of this in the same test function. Let's copy this for now. Here. file IO, and we every time we say IO base, we say file IO. This is a bit too close. It's a bit too repetitive here. Subclass with del, not of IO base, but of file IO. I hope it's there. Check. File IO, yeah. And the rest is the same. Yeah, it's a bit weird. The fact that we have basically identical. Yeah, there's too much copy pasting going on. But let's try to pass it first. It may even already pass. But it's good to have this test. It's like an eat your greens kind of test. Here. File IO. Let's wait for that. Okay, that doesn't work. Why does it not work? I know, because the file IO needs some kind of name, I think. Right, it's this code that fails, and I suspect that it's this call here. Let's see. OS error. It really needs a file name, right? That makes some kind of sense. What happens if I do this? That may or may not work. Right, doesn't work. So we need to pass in an acceptable file error, and we're going to pass in the current file. And I mean, this weird stuff here is because it's a function, so I don't even want to explain it. It's obscure. I mean, this is a somewhat obscure testing sort of gadget that you can use to call to run Python code on top of your interpreter when you're running test functions that run on the RPython level, on the level of the Python 2 code, the interpreter level code. Right. So it passes. We don't need to do anything. The reason why we don't need to do anything is because the close implementation here is actually done in a nice way, and it calls the base close properly, right? And the base close will actually do the unregistering for us, so we don't need to change anything here. Right, so this stuff is good. And I'm going to write this a third time for buffering. I think maybe I don't even want to. I would really like a little bit more of a functional test. One that really says, if I use open to open a file, and then it will construct the tower for me, and I don't want to get any calls to makeignore. And no, I do want to get a number of makeignore finalizer calls. Let's try it. So if I run, I don't want to construct these things by hand. I wanna really say, if you f open file name for reading, and I can say encoding is UTF-8, then I will get buffering and decoding, and so it's like a tower of 3 objects. And if I then close it, then I want to see calls to it. I need to think, yeah, I want to look into how many calls I'm expecting here, but I can also do this thing, return F. Yeah, let's get a debugger and look around. I'm a fan of this approach. Just if you don't completely know what the state of your objects is, you can sort of construct them in your test and then start a debugger, And then in the debugger, you can sort of inspect your, yeah, I'm running the wrong thing. Then you can inspect the objects and try to see what's even going on. It's kind of a, yeah. It's like a bit of a small talk-like approach or something. Right. So what happens here? Wait, okay, I want to do this differently. I want to run the test with PyPy because I'm trying to get myself to only use PyPy 2 in development because CPython 2 will go away eventually. And I'm doing that by not installing the nicer debugger on CPython. That means every time I try to debug something, I'm reminded of, please don't use CPython. Right, so now I have the PDB++ instead of PDB, and I can say, what kind of calls do I have here? Wow, what? I did not expect this. Okay, why? So apparently, in the meantime, like to get from here, like between here and here, many things had their finalizers ignored. Like some generators and several files and some generators and a file and a generator. And do they repeat? Like what's the set of this? They don't even repeat, right? So something does a lot of work here, and I think it's part of the magic. So let me actually try something. What happens if I do this before monkey patching and then I do it a second time? Oops. Maybe I see somewhat less noise. I mean that's kind of the downside of this monkey patching and then checking that we see calls approach, because it really means that yeah, it's a bit brittle. So like if somebody else calls this API, then yeah, then you see calls that you don't expect and you're slightly annoyed. Right. Yeah, this will make the tests look somewhat weird. I need a comment to explain the weirdness at least. I'm a bit confused why does it not happen here? So it seems to really be open specifically, maybe. I don't know. I don't get it. But I'm fine with that basically. It's not fantastic, but okay. Wait, no, I shouldn't have quit that. Right. So now we're back to seeing one call, and we're seeing a call to the most underlying object in the stream tower, which is the file IO object, right? That's what we saw here. We see a call to the file IO here, but the file is actually a stack of things, and we want to see calls to unregistering the dunder del for all of them, not just for the file IO one. So actually, so what I'm saying is that the calls is too short. We want more things here. In particular, we want this has a close, right? And this should have triggered one call. And then what's the next here? There's many things, but in particular, it has a buffer, right? And a decoder, right? Does it have a close? Does the decoder have a close? No, it doesn't. Only the buffer has a close, right? So that's a buffered reader, and that has a raw, I think. Is it called that? W raw, right? And that's the file. And so we saw the call only for the third one, while we want to see it in all three objects of the stack. So we want to say something like assert in calls and assert wf dot, what was it? W buffer in calls and assert wf dot buffer dot raw in calls. I think this is what we want to achieve here. And we only get it for the last one, and so that's what we need to fix. And so now we know for which classes to fix it. We need to fix it for wait, what is WF again? We need to fix it for the text.io wrapper, and we need to fix it for buffered reader. So let's open interp text.io. I think the thing to do here is, so what does it do? It checks whether we're closed. If we're closed, we're done. Otherwise, we call flush, and if we get an error, we call close. If we don't get an error, we also call close. And right, we can't unify the code because of the chain exceptions. And then at the end, we want to say self.may unregister finalize IO. I'm not so happy with this method name here, but we can change it later. Space. Right. This should take care of one of the things in calls. So now we should have two things in our calls list in the test. And now we should also do it for what? Buffered IO something. Def close. How many close implementations do we have? That's the buffered read-write pair. I don't care about that. Yeah, the buffered mix-in is the one that we want. And I think it's the same basically. We say if we're closed, we return, and so then we flush, and finally we close, and right. And at the end we can say self.may unregister space. Right. Okay, let's try it. This should maybe pass. It does. Amazing. That's cool. I'm happy with this. Right. Good. Let's commit it. Okay, so I wanna rename this function because I mean, I'm of the opinion that even the default one is badly named. Let's look at the default one again. It should be because it sounds like the caller decides whether you can unregister the finalizer, but that's not really true. It's more that you tell this method, if that is legal, please ignore it. But yeah, so I don't want to globally rename it, but I don't want to repeat the slightly weird naming. So I'm going to call it maybe Oops. And it was also in buffered IO and in text IO. No, in file IO, right? Okay. So now we should run all the tests. And then we could, so there's one problem. I mean, it's the usual, I mean, not the usual, but it's one of the annoying parts of working with, no, wait, okay, I'm getting, so one of the annoying things of developing PyPy is that compiling to C takes ages. And that means on the stream, I mean, usually I just do something else, right? Like, usually I start a compilation and then go away for 45 minutes and then we can, work on something else. But here on the stream, it's a bit annoying because like going away for 45 minutes isn't very good watching. So often we start optimizations, but then we cannot really observe the effects. And I think this is something that will probably happen to us tonight. But I'm going to start a translation anyway. So I want to translate it without the JIT and no shared and output unregister finalizer. And we can start it, and then my poor CPU is going to be even more busy. Right. The tests run. Right, so now some waiting is involved. Yeah, this was a spelunking a somewhat strange part of PyPy, but yeah, it kind of needs doing. Actually we can probably learn other interesting things here, because I suspect that all of these close implementations, they're generally terrible, right? Right. So here we have the buffered random close. Right. And here's the file close. I mean, they do all these things, and they do very complicated, difficult things. And right. So once the current thing, once we're done optimizing the current thing, it's entirely possible that the next thing that's slow is the fact that these close methods are implemented in very bad ways. And what do I mean by that? If you look at right, we call these flush. We use the space API to call flush here, and this call to flush will very likely end up going here, which does not a lot, but it goes through this API, which is basically the way that the interpreter is implemented, and that's very indirect and very inefficient. So here is probably not so bad, but I think in buffered IO it looks pretty terrible. We do check init. Oh, is check init done? No, that's fine. and then we do, oh, damn it. Check init, then we get the lock. That's okay. Right, that we go through the space again here as well. I thought we fixed that. I thought, yeah. Sorry, I'm rambling to myself again. Right. We have a excellent. Well, not good really. We have a problem. One of our tests fails. One of the tests that we wrote fails. Right. So what's happening here is that bootstrapping to C is proceeding slowly, and that will produce these. If you've never seen that will produce these nice Mandelbrot fractals in the terminals. The first one is the most easy to see that it's indeed a Mandelbrot, and we will just keep that running. But our test is bad. It's not even the implementation that it's a problem, but the test is a problem. And I don't really know why it started failing now, but we need to look into it. Right. Specifically, this one fails. And I think it fails, it probably fails for the same reason that that this one used to also fail, right? Yeah. I need to do something about these tests. They aren't in good shape. I mean, there's too much copy pasting going on, and yeah, they fail because we see a bit too many calls to the thing that we're trying to not see. So yeah, we need to do something about it. And we're waiting for translation to C anyway, so we can do that. Yeah, as you notice, we're sort of. I mean, I'm not completely winding down yet, but the main task is done, and now there's waiting involved for us to be able to see whether it helped or not, and so we can like do some cleanup work and look around a little bit in sort of related areas. Right. So yeah, so what I want to do is I want to do some cleanup of the copy pasting here, and I wanna like write the test in a little bit more of a robust way. Because this test is extremely strict, right? What this test checks is that from here to here we do not see any calls to this function, right? But that is a way. I mean, that test is way too precise. We were actually happy enough to know that this instance here never is called, is never passed into main-ignore finalizer. So we can return this new instance of the newly created subclass. We return it we return it out of the interpreter into the test function. We call it WS, like a wrap thing, and then the assert becomes a lot less strict by saying we want to make sure that this is not in calls. And we don't really care what other things are in there, as long as we make sure that this thing definitely must not end up in calls. And I think similarly here we want to say we return the instance of the subclass with del of file.io. It's already closed, but we want to make sure that and that is a good improvement, because it's less brittle and it communicates what we're trying to say in the test much more precisely. The thing that we really want to test is we want to make sure that we do not call main-ignore finalizers on this instance here. Right, so that's good, and that should also make our tests pass. Right. The other thing I want to do is I want to reduce the copy pasting slightly. I do that by saying monkey patch calls equal monkey patch may ignore finalizer, and at least put that into its own method. Oops. So this goes away, goes here. This could probably be its own PyTest. What are these things called again? Fixture, but yeah, I'm not too firm on advanced PyTest programming, so I do it in this boring way. Right, so it gets slightly shorter. And the import can go. So let's remove some copy pasting here as well. I think this is fine now. This can go. Right. This looks somewhat better. Okay, let's see. Should still pass. Yeah, and then we should be somewhat better citizens, and we do some monkey patching here to log calls to the underlying function, but then we don't actually call the underlying function anymore, which is not really a problem, because I think if you run this function without translation, it really does nothing, but it's slightly iffy to not do it. So we get the original function, may ignore finalizer, and then in our monkey patched function, we actually do a call to oric func with the argument. Right. Ooh, not good. Okay, no, boring. I forgot the return calls here. It's a much more benign way for this test to fail. On first reading, it looked like the calls list was empty, and that would have been a bit scary. Instead, it was just a typo when refactoring the monkey patching. So waiting. What does the computation do? Yeah, it's on the second step. I mean, experienced PyPy devs can see in which phase we're in. I mean, it's the problem with bootstrapping to see it's that it's completely non-incremental, and all our attempts of, I mean, it wasn't designed to be incremental from the start, and that turned out to be one of the worst mistakes that the PyPy project has made. Because you need to wait for like 45 minutes every time you really need to check test the bootstrap to C binary of PyPy. And since we're waiting on stuff anyway, I can talk about the phases. So the first phase does type inference. So it will basically take the whole RPython program and try to infer all the types that you're using in the program. So it will look at all these functions and say, okay, what is self here? What is space here? Which function does the underscore close method refer to? What's the type of this attribute, and so on. And then it ends up with a complete call graph of all the reachable functions and all their argument types, return types, and local variable types, as well as all the classes used and all the methods used and all the argument and return types of those, and all the inheritance hierarchy and like the types of all the attributes and so on. That's the first step. Like that's the first phase, and that takes a few minutes up to here. And then the second task starts, and that's basically a transformation pass. It takes all the information from the first phase, and it changes all the control flow graphs to operate on a much lower level that's close to the C level. and then basically in this more lower intermediate representation of our Python functions, we do some optimization. That's optimizations. That's the third step. And then the fourth step is actually just turning them into C code and calling the C compiler on that. Cool, our test passed. That's good. So. Right, I think that's the things we did. Right. We should push this. Cool. Yeah, I think we're winding down. We can. This probably takes a bit too long for me to feel like waiting for it. What did we do? We discovered by looking at the profile that the problem when opening and closing many files is actually that the dunder-del takes a lot of time. And then we looked at the PyPy 2 and to find out why in PyPy 2 this is not a problem. And it turns out that on PyPy 2 there is some special special API called in the garbage collector that says, I am sure that you don't need to call dunder-del on this file object because it was already closed. And it turns out that this implementation, this optimization isn't there on PyPy 3. And it's not, the reason why it's not there is because the file implementation changed completely between CPython 2 and 3, but also PyPy 2 and 3. And so we started and implemented the steps necessary to also call this GC API that tells the garbage collector to ignore the dunder-del in PyPy 3. And now we're basically done. And now, I mean, the remaining work is running the build bots to check that we didn't introduce any regressions, which, I mean, that's possible, right? This is a slightly dicey area, and I'm not completely sure I oversee all the interactions of, oh, somebody subclassed this weird stream class here and then has a very strange del here. So we should definitely run the CPython sort of library test suite. Let's actually kick that off. We can kick that off. So I go to the build bots and I go to the builders and say, please force some builds. And we should force the builds at least on Linux 32 and 64. I don't think we did anything operating system specific. We can also run our own tests. And then you need to give your name. And what's the branch name again? Right. Pass the branch name. Right. Now we'll start the tests and so in our IRC channel there's a bot that announces that the building has started here. It will also tell me when the build bots are done, and then we can look at the results from that branch and find out whether we broke something new. But that's also going to take like an hour, so we can't do it. Like, I don't want to wait for it. And the other thing we can do, so we're talking about the full life cycle of branches, and so one important thing that we need to do for the branch is to actually document the branch, and that's done in this file here. That's like the raw material for the next release announcement, and gives like the changelog. And so every branch that's merged should be documented here. Right? The ARM chat in general points to the link of the CI pipeline. That's actually, yeah. So we have a fairly strange CI setup. I mean, we don't really use. So those are the CI pipelines of Heptapod, which is our GitLab fork, not ours, but the GitLab fork that we use that's changed in such a way that it supports Mercurial, and that also has a CI system that's like a fork of the GitLab CI system, and those have some very minimal test pipelines that are run on every push, right? And they're basically a smoke test that makes sure that things aren't completely broken. But then, and all the quote-unquote real testing is actually done on our own infrastructure, which is a build-out instance. And the reason why we don't do it on every push is that it's done on many operating systems, and on it just takes ages, right? We cannot afford, we don't have enough hardware or building minutes to do it on every push. So we do it nightly on a certain number of branches. We do it nightly on default, which is the PyPy 2 implementation, and nightly on 3.7, but yeah, we cannot afford to do it on every push, so we do it once a night. And that will also, like, yeah, we can look at the failure display. Yeah, the build board is a bit slow. I noticed the same thing yesterday. Yeah, some stuff is failing, so you have these Fs here. That's not great, of course. There's some stuff failing on ARM, some more. Mac has a few failures, and Windows is our least well-supported platform, and it tends to have a number of failures. And yeah, this test failure, so the 5 Fs you see here that means that it's been failing since 5 nights. Whereas this test has been failing 4 nights ago, and the reason for that is that this particular test tends to very occasionally fail. And this test basically means, yeah, it means that so CFFI is developed in its own repository, and occasionally you need to sync them. And this test actually says you haven't synced the repositories, and please do it. And nobody actually went and did it, so that's slightly bad of us. Right. So yeah, the other thing I was talking about is the what's new entry. So we should document the branch here, but by now I forgot what it's called already. What was it called? This. So let's document the branch. Right. Okay, that's good. So we should check that in. Yeah, CPython has a more sophisticated tool for this job, because it turns out that if you do it via file, then you tend to, like, if you have many active branches at once, then you tend to have merge conflicts in this file a lot. So they have a system where you just I forgot what it's called. But you have a system where you produce a news entry which is in its own file, and then there's a process later that merges all of them. Right. So we're now in the next phase, but I think I'm basically done. If there aren't any questions, then I'm going to end the stream, because yeah, this would take another 15 minutes or something, and I'm a bit too tired to wait for that. And yeah, maybe I'm going to do it like last weekend. Last weekend I recorded a small update on Sunday morning when I had fixed and and benchmarked and tested the change of the stream last Saturday, and added it to the YouTube upload. I might do that tomorrow as well. Push that. Right. Yeah, I can spend 5 more minutes reading the close here, because I really think that those close, I mean, maybe it doesn't matter because you tend to not open hundreds of thousands of files, right? Maybe it's fine that the close is kind of inefficient, but it is kind of inefficient. There's one thing about there's one immediate thing about close that we could make faster. I mean, I'm not going to do it. I'm just noticing there is a mechanism for making the close check. I mean, checking whether the file is closed needs to be very efficient because you do it on every read, right? On every read you check, is it closed? Is it closed? Is it closed? So and that means if you like iterate over a file line-wise, then you would do the close check on every write. So on every line, and that means you really want that to be slightly more efficient. But that is only done in the check closed method here, right? So check closed is called from stuff like read. And that has a fast implementation of closed checking, but the actual close method doesn't use it. The actual close method, wait, where is it? Here, that doesn't call check closed. It calls underscore closed, right? And that is actually a slow implementation. So it might actually make sense to use the same fast implementation here and in check closed. Let's actually try that. It sounds good. I'm not sure it's safe, but yeah, I'm not doing. I'm reversing my opinion. I'm not going to do it now, but it's something to keep in mind that basically the close method itself is inefficient, and it's possible that when this is done and we reprofile, we will see that now the close method itself, now it's no longer the GC that's the problem. Now the close method itself is much higher in the profile, and then we have to go look at that and profile it, because right now the close method is not high up in the profile. Right now the close method is here, very far down here. But it might end up being much higher when we optimize the rest. I mean, that's a common thing to happen, right? You have slow stuff, you optimize the top entries, but then other entries are top entries, and it might be worthwhile to optimize the new top entries in the profile. Right. Okay. Yep. I think I'm done. Yeah, that's it from me. Thanks everybody for attending. I'm going to do another stream next Saturday, I think. And that was fun. Talk to you all later, and have a good weekend. In Germany, it's even a long weekend, which I can really use right now. So, thanks everyone. Goodbye. Yeah, I should have waited some longer, because just a couple of minutes later, the compilation actually finished. So I'm going to try to see what the result looks like. So this was our state. Opening and closing a million files took. Let's see. No, we need to do this differently, because I compiled a version without the JIT, so I should actually do this. How long does that take? 500,000. Opening and closing 500,000 files takes 7 seconds. And now the compiled version that we just built with the changes from the stream. No JIT, right. Open many 500,000. It's faster. It went from 7 seconds to 4.76 seconds. Let me remind myself how long CPython takes. This is not the 5x speedup that we need, I think, but it's definitely a good start. Right. So let's use the profiler again with less iterations, 10,000 files maybe. Let's see. Right. Most importantly, we do not see the garbage collector here anymore. So before we had, this is the PyPy 2 version. Let's look at the PyPy 3 version briefly again. Background, okay, cache grind. Should be this one. Yeah, PyPy 3. We had, when we sorted by self, we had deal with objects with fin. Right, so when I search for deal with, it doesn't even, we don't even call that function anymore. That's great. And also visit all objects step. Visit all objects. There's no major collection at all happening anymore. So that's really good. It means that what we were trying to achieve worked. But now, of course, the next step would be we would have to look into what are the things that we do now. Like what is the expensive bit? Right. And now basically the allocation of the objects is the thing that takes a long time, right? We basically creating a buffered reader is yeah, what takes ages. Why does it take that long? Buffered reader init. I mean that basically goes beyond like what we set off to achieve, but still kind of interesting. It's probably the buffered reader mix-in. No. Right, there's an init here, and this init takes ages apparently. It's not quite clear to me why. So there's an alloc and set call here, which basically allocates something, and I kind of suspect that there an init here that takes long? Yeah, we make a dict. Making a dict always takes time. We could do that lazily. That's an obvious idea. We can try. Anyway, that's not what I'm here for now. But basically, now we would have to go back and look at the profile and see what other things we can improve now. Right. Yeah, we spend a lot of time in open now, which is more expected. Right here, 60 units is in open, and here open. No, also 60. Interesting. If it's percent, then not much change, but I don't think it's percent. Okay. Anyway, I just wanted to very briefly talk about the fact that what I was planning to do actually worked, and that's cool. And now basically the next step would be to merge the branch if the test run shows no additional test failures. Yeah, that was the small post streaming edition from me. Thanks for watching if you're watching this on YouTube, and I stream on on Saturday night, 8 o'clock Germany time. So join me if you want to. And see you later. See you all later. Bye.